Today's lecture will focus on calculations related to pH. Specifically, we'll learn how to calculate pH from hydronium and hydroxide. We'll learn to calculate hydronium from pH and work some example problems. In the past couple of lectures, we focused on pH scale, setting up this process of determining pH. And you've had some focus on that in lab. Let's go ahead and look at our formulas here. pH is equal to the negative log of hydronium. Remember that hydronium times hydroxide is equal to 1 times 10 to the negative 14th. Okay, so we can find out hydronium if we know hydroxide and vice versa. Likewise, if we want to calculate hydronium from pH, it is the inverse log of the pH. And I'll talk more about what the logarithms mean in just a minute. Note that these are all on the log 10 system and not natural log, so it changes the calculation just a little bit. Looking at the scale over on the left-hand side, we see things all the way at very low pHs, like gastric juice compared to ammonia and sodium hydroxide solution. A couple of things to note here, and this has been said in other presentations, but not quite the same way, that for an acidic solution, pH is less than 7 and hydronium is greater than hydroxide. In a basic solution, pH is greater than 7 and hydronium concentration is less than hydroxide. In the next slide, we'll look at the log system and how to round these pH calculations, and then we'll get directly into some example problems. In this particular slide, we look at the relationship between hydronium ion concentration and pH. I've made mention in a previous presentation that we look at the exponent of the hydronium concentration to give us an idea of pH. Okay, the reason for that is if we look at a number like 1 times 10 to the negative 4th. Okay, what this is telling us, this exponent tells us the position of the numeral relative to the decimal. Right, so we have 1 times 10 to the negative 4th. If the exponent is negative, then the number is to the right of the decimal. And we're going to be dealing with that case when we're looking at pH calculations exclusively. So that tells me that the 1 is 4 positions to the right of the decimal. So that's the same thing as 0.001. Right, in pH, the pH of that particular solution would be 4. Okay, if the numeral is right on 1, then pH is equal to the exponent. Specifically, it's the negative exponent. The way we round pH calculations is a little bit different. If we look at the rule here, we take the number of significant digits from our hydronium concentration and we round pH to the number of places after the decimal. Right, so let's look at an example here. We're given hydronium concentration is equal to 1.00 times 10 to the negative fourth. Right, this particular number, those zeros are significant, so there are 3 sig figs. So our pH should have 3 digits to the right of the decimal. In this case, I don't have to do the calculation because the numeral is 1, so it's right on the pH value, right on the exponential value for pH. So I know that pH is equal to 4.000, 3 digits because of the 3 significant figures. I know I can estimate pH from the exponent. But I need to be able to calculate it more precisely. So let's look at a couple of examples. Hydronium is equal to 1 times 10 to the negative 8th. We'll do another one where we have 1.7 times 10 to the negative 6th. And then let's look at an example with hydroxide. Hydroxide is equal to 2.4 times 10 to the negative third. All right, so let's calculate this. In the first case, pH, so this is number 1, pH is equal to negative log 1 times 10 to the negative 8th. All right, so I can put that into my calculator, but because I can use my estimation here, this first number is 1, then I know pH is equal to 8. And my answer should have, I've got 1 significant figure in hydronium here, so I need 1 digit to the right of the decimal. So pH is equal to 8. Well, let's look at the second example here. This time I'm going to have to plug and chug. pH is equal to negative log of 1.7 times 10 to the negative 6th. All right, so the way that I put this in my calculator, if you have a graphing calculator, you can go ahead and put in the change sign and log, and then put in the number in parentheses, so the number, EE, negative, and then the number again. Enter. In my calculator, my lesser scientific calculator, you have to put in hydronium first. So I would have to put in 1.7 EXP, change sign, 6, and then log and negative again. All right, so let me go ahead and calculate that. I know it should be somewhere between 5 and 6 if I do my calculation correctly. And I'm getting pH is equal to 5.77. So we need to look at how many places to the right of the decimal. My hydronium has 2 significant figures, so my answer should have 2 places after the decimal, so that'll work just fine. All right, let's look at another example. In this case, we're going to be dealing with hydroxide. So there's a couple of different ways we can do this. I'll show you what I think is the easier way. Instead of calculating pH, we can calculate pOH, which would be negative log of hydroxide concentration. So that would be negative log of 2.4 times 10 to the negative 3. All right, I'll go ahead and put that in my calculator. And I'm getting, that's two significant figures, so 2 places after the decimal, 2.62. All right, that's pOH. Let me go ahead and erase some of this other side over here. And it is not letting me do it today. I haven't quite figured out when it will let me erase and when it won't. I know that pH plus pOH is equal to 14. So 14 minus 2.62 pH is equal to 14 minus 2.62. And I'm getting 11.38 as my final answer there. All right, so we looked at calculations from hydronium to pH and hydroxide to pH. Now let's look at the reverse situation. Right, in this example, we're going to look at the inverse process where we have a pH and we want to convert it to hydronium. So going back to our original formula, pH is equal to negative log of hydronium. And so to isolate for hydronium, you would divide both sides by negative log. When you do that, you rewrite it as 10 to the negative pH, or the inverse log, is equal to hydronium. All right, so let's look at two different pHs. pH is equal to 4.6, and pH is equal to 10.8. Right, so from looking at them, I know the exponent for the first one, it should be somewhere around 10 to the negative 5th. And in our second example, 10 to the negative 11th, if we're looking at the closest whole number. All right, so let's set this up and work this problem. Hydronium is equal to 10 to the negative 4.6. All right, so again, if I have a graphing calculator, I can go ahead and put in inverse log and then change sign and my number equals. In my calculator, I have to put 4.6 and then the negative change sign and then inverse log. All right, so let's go ahead and plug and chug. And I'm getting 2.51 equals 2.51 times 10 to the negative 5th. And going back to my pH, I had one place after the decimal, so this would be one significant figure. And so I would have to round that to 3 times 10 to the negative 5th. Okay, let's look at the second example. Hydronium would be equal to 10 to the negative 10.8. Right, so plug and chug. I'm getting 1.58 times 10 to the negative 11th. Right, so going back to my pH, I have one place to the right of the decimal. And that would give me one significant figure. So this would round to 2 times 10 to the negative 11th. All right, let's take a look at another example. In our last example, we'll be filling out this table, and for convenience sake, just talking about the rounding here, all of the pHs will go 2 places after the decimal because we have 2 significant figures that we're going to use in each of our hydronium or hydroxide. And then lastly, we'll consider something acidic or basic. Right, so let's work through this set of problems. Let me see if I can move this up here just a little bit. All right, so let's look at row 1. Hydronium is equal to 3.5 times 10 to the negative third. To find hydroxide, that would be equal to 1 times 10 to the negative 14th divided by 3.5 times 10 to the negative third. And I'm getting 2.9 times 10 to the negative, well, I must have hit the wrong button. Let me double check that. .9 times 10 to the negative 12th. Right, pH is equal to negative log of 3.5 times 10 to the negative third. I'm getting 2.46. So this is an acidic solution. The pH is less than 7. All right, let's look at the second example. We're given hydroxide this time, so we'll be solving for hydronium. Hydronium is equal to 1 times 10 to the negative 14th divided by 3.8 times 10 to the negative 7th. All right, and I'll put that in my calculator. I'm getting 2.63 times 10 to the negative 8th. So 2.6 times 10 to the negative 8th. pH is equal to negative log of 2.6 times 10 to the negative 8th. And I am getting 7.58. So for this particular solution, the pH is a little bit higher than 7, so it would be considered basic. All right, let's skip through this third example here. You're going to do some more in class, so we'll focus on the one that is the reverse problem here. All right, I'm going to go ahead and we'll see if it'll let me erase. Okay, this time it did. All right, I'm given pH and I want to calculate hydronium concentration is equal to 10 to the negative 7.15. And I'll plug that in, inverse log. So I'm getting 7.1 times 10 to the negative 8th. Hydroxide would be equal to 1 times 10 to the negative 14th divided by 7.1 times 10 to the negative 8th. And the answer is, I must have hit the wrong button there. Let me retry that. I'm getting 1.4 times 10 to the negative 7th. And I already know that this is slightly basic because the pH is greater than 7. All Right, so the focus in this particular section is the calculation of pH, hydronium, hydroxide, and then we did do one example with POH. If you have any one of these, you should be able to work backwards and find the other three variables, and as well as knowing if the solution will be acidic or basic. Activity 15.3 will focus on these types of calculations.